Hey folks, welcome back to MedTech Unboxed. Today we're talking about medical balloons. They're used from plain old balloon angioplasty to the delivery of complex structural heart valves. And behind every balloon, there's a manufacturing process. And that's what we're going to talk about with today with Nate. Nate gave an excellent presentation at the recent MPP East talking about the journey from and the balloon forming journey. And I thought I'd have Nate back on to share that platform with a broader audience. So welcome to the show, Nate.
Yeah, thanks, Steve, so much. I had so much fun at MPP East. Great venue and everything, overlooking the Boston skyline. And I'm really excited to kind of share more about balloon manufacturing. I think it's kind of an unsung hero of medical devices. There's so many implantables that are dependent on balloons, and we kind of get a bad rap of being the odd ones out everywhere we go. So it's really excited to bring some more light into balloon manufacturing here.
Yeah, that's exactly why I wanted you to have it. It was such a great presentation. I took snapshots of it, but like I said, let's just get them on the podcast to talk about it. And in a minute, I'll let you share your presentation. But just before we even do that, why are balloons harder than people think? I mean, I think a lot of people believe that you take any old extrusion and just blow it up to a balloon, but it's much more complex than that, right?
Yeah, it is a lot more complex than that. Now, I'll speak a little bit to that in the presentation, but kind of at a really high level, we talk about all these engineered plastics and engineered materials that we're introducing into the catheter space. And, the same thing goes for balloons, right? It's really highly dependent on the material and that you have. And we really push the balloons all the way to the limit of the material capabilities, and it's because we're pushing it all the way to the limit that it becomes really difficult. We're so dependent on material and the consistency of the material that you receive, and the capabilities of that material as well, right? And so when in catheters, right, we talk about maybe the heat history of the material, how many times we reflow it, how long is the residence time inside of the extruder. And that impacts the performance of the shaft. Well, the same thing is true for balloons, and even more so, because we never really fully melt it after it leaves the extruder. So it's really a highly critical, really highly critical that the material is consistent, and that it's in our case, we prefer it to be as stretchy as possible. And then further down the line, we want to make sure that we don't have any any negative impact in the operating room, right? When doctors are using and inflating balloons, we want to make sure that they're inflating the same across every device, and that we have good deployment for stents and valves, and good occlusion for vessels when we're talking about compliant balloons. They need to be functional 100% of the time. We can't have a single one that's a single failure at all. I don't know about you, but I don't want the balloon exploding in my left ventricle.
That'd be an issue. Yeah.
Yeah.
And of course, I'm biased here. I know the kind of the foundation of this is extrusion, right? And having a good
Yeah.
input. So I'm happy that you're going to be walking us through that as well. So Nate, why don't you go ahead and share your slide deck, and please walk through that presentation, which was excellent. I know everybody's going to enjoy it.
Yeah, absolutely. Let me pull it up here. All right.
There you go.
Can you see it in full screen?
Yep.
All right, cool.
That's great.
Yeah, well, we at MPPEs, we titled it "Under Pressure: The Hidden Challenge in Medical Balloon Manufacturing." I did need to fulfill a little bit of a marketing requirement here to wanted to make it sound a little catchy.
Good work.
Yeah, just a little bit about myself. I was doing I started out kind of in the tipping and hole forming equipment design and development over at Cath Tip, and then I transitioned over to implantable leads at Proton MedTech and Singular Medical, working on a tachycardia lead, bradycardia lead, and then currently, working for a couple of years on balloons at Switchback, and I'm now the director of balloon technology at LightningCath. We're working on standing up our new balloon component department, where customers will be able to come and order balloons from us at a component level, and we can then integrate them into larger balloon catheter systems, either here or at our customers' facilities, whichever ones they prefer. I really want to start by kind of explaining a little bit about the medical balloon manufacturing journey. And I really do like to think of it as a journey, because the balloon has a start, it has a finish, right? There's a whole lot of process that that go from, getting a plastic pellet to your final balloon that gets bonded onto your balloon catheter. Everything starts with extrusion, taking the pellets and then running it through your screw extruder. We use US extruders here at LightningCath, but that getting it into a tube form is the first step. And there's certain complexities with that I'll kind of run through in the next few slides. From that, we take our extrusion and we throw it into our balloon blowing machine, and we go through a blow molding process where we pressurize it, heat it, and stretch it in order to form the balloon. And then finally, testing is super critical to make sure that the lots of balloons that we're releasing here are all meeting, the requirements that are set by our customers and further, by the FDA. And making sure that we're hitting those high standards, so that there isn't a single failure out there in the field. Just to give a little bit of overview on the extrusion, kind of the three most talked about materials that are used for medical balloons. You got your nylon 12, your PVAXs, and your urethanes, like polyethylene essentially. Up on the screen here, I have shared the dimensional requirements that we try to maintain. So the ID within 1.7% of the nominal ID, the wall thickness within 5% of the nominal ID, or wall tolerance, I should say, and the concentricity of greater than 90%. The ID is really critical to our ability to expand the extrusion to the balloon diameter. Right, this is where the mechanical properties of the tube are so important, because we can only stretch the tube so much. So maintaining the ID is really critical. And that ID tolerance is super critical because we develop our process around a certain expansion ratio for the balloon. And if that expansion ratio changes too much, then all of a sudden we need to start changing our stretch and our pressure parameters, which leads to process variability, which is highly undesirable in the medical space. The wall thickness and concentricity is essential to the burst performance. We in manufacturing, we measure the double wall thickness, and that's directly related to the wall thickness and concentricity of the tube. If the tube is eccentric, then all of a sudden we get a thin spot on one side and a thick spot on the other side, which is problematic. And if the wall thickness is not right, or it's outside of the tolerance, then our wall thickness isn't going to be right with our validated process, and then we're going to have a thinner balloon or a thicker balloon, which is undesirable as well. Talking a little bit more about that concentricity. Here, you can see a picture of a pleated folded balloon, right? And in any one spot, you can see that there's maybe 5 or 6 layers of material there. And so if you have a small deviation in your wall thickness, right? Like let's say you have an 80% concentricity, and you're maybe you got a half thou difference, right? If that, let's say, right, a half thou difference between your thin side and your thick side. Well, that means that on one side of your balloon, right, on one side of your catheter, you're going to have an additional half thou multiplied by 6, right? So additional 3 thou, which drastically can change your crossing profile. When you're talking about the size of small catheter delivery systems, your balloon catheters. So kind of just running through this, right? Your eccentricity leads to a thin side and a thick side. The extrusion, right, means you have a thin side and a thick side of your balloon wall. And then, we have to increase our overall balloon wall thickness to maintain a minimum wall thickness so that we have the same burst resistance. And doing that changes the compliance performance and then the pleat and fold tolerance stack up as I kind of just ran through here. So it's kind of interesting how such a small change in your concentricity could lead to such a big impact in your device design and then further in the performance of it in the doctor's hands as well.
Nate, quick question.
Yeah.
In balloons, and one thing I noticed in balloons, difference in extrusions and balloons, we talk about wall thickness, but in balloon terminology, you talk about double wall thickness, and you covered a little bit. Can you just dig a little deeper into that?
Yeah, absolutely. One of the most common inline checks that we do is measuring the double wall thickness, where we flatten the balloon and use a drop gauge to measure the thickness of both walls of the balloon. It's a non-destructive way for us to measure, to measure the wall thickness of the balloon, because it's pretty difficult to measure the single wall of the balloon. There are ways of doing it. People use lasers, ultrasonic. You can even throw if you have it, you can throw a steel bead in there and use a plastic wall thickness measurement, like a magnetic gauge to do it. All those are kind of, involve big setups, and they're tedious, and kind of expensive to do. And so, some people do them when you absolutely need it. But most commonly, we just flatten the balloon and measure the double wall thickness as an inline check. If we're really trying to characterize it when we're doing our process development, we'll cut the balloon in half and measure the single wall. But measuring the double walls is usually good enough. We take 3 measurements on the balloon, right, on the proximal side, the medial, and then distal side. And then we can even rotate at 90 degrees and do the same thing. That kind of gives us an idea of how even the wall is around the balloon too.
Thanks for sharing that. I always wondered why they referred to double wall, but that makes more sense for non-destructive testing.
Yeah, absolutely. The other thing I mentioned a little bit about was the criticality of the tensile and elongation, or the physical properties of the tube. I just want to share a little bit here. You're looking at is all samples of a nylon 12 stress versus strain curve. And one of the common terminologies that's thrown around out there is, we want to measure the ultimate elongation of the tube. What's the significance of that, and what does that actually mean? So when we start measuring the tensile and elongation, and we kind of took a step back and said, all right, what are we actually looking at when we're looking at balloon blowing? And what do we look at for the tubing requirements? And what really came out was the strain hardening onset that I'm going to highlight here. So if you think about your stress strain, right, you have your instant spike. This is your yield point here. You go through a necking region, and you encounter this dip here, which we're calling our strain hardening onset, and then this, rise up until the ultimate elongation of the tube. Anything beyond this strain hardening onset is already the area of material degradation, where the material is starting to break down. Molecular molecules are starting to separate from each other. You might see like a little, I don't know, little I don't know what you want to call them, little scraggles or lubners or whatever you want to say, that like start separating from the tube. Which is all really undesirable. And so then when we took that and we tried to correlate that with our, balloon stretch ratios, we saw a pretty good correlation between, this strain hardening onset and the maximum stretch ratio that we're able to maintain on a balloon. To kind of give you a visual of it, if you look in this bottom right corner here, right, this is a tube right off the line, right? We've marked off a 1-inch section of that tube, and then we've stretched it until it's necked all the way through between these 2 dots. And the difference between, or the ratio between the distance after it's been necked and the non-neck distance, that's the significance of our strain hardening onset. And this is really kind of a different way, or the way that we're kind of interpreting that maximum elongation of the tube. And it's been working really well for us. So hope that's helpful to folks out there too.
Is that critical, Nate? I know in at least nylon 12, there's a certain elongation percentage that you want to hit for compliant balloons, ultra compliant balloons, TPU, lower diameter PBACs. Is that still something that you look at as much? Is it critical?
No, this is more for really for the nylons.
Okay.
And the significance of this slide is I really want to just try to communicate that I want people to always remember that you want to be inspecting the things that are important to your process.
Yeah.
Right. And so when we were experiencing gripper slip, right, and breaking at the grippers, that was a real indication to us, like, well, do we really need to take it all the way to the maximum elongation? We're not even sure that we're reaching that, right? And it's super test method dependent. So really just bringing it back to, what are the essentials and what's critical to our process? And this is what we found to be critical. For the polyethylenes and your compliant balloons, you're actually not going to see this same type of graph. It's going to be much more like a rubber. So you'll see it constantly increasing in strain as the stress is going up until it breaks. You don't really see this necking region when you're doing your tensile test. And so I'll actually kind of talk a little bit more about that in our kind of a couple more slides here, but it's a little bit different. And so we look at things more like the modulus and also its ability to expand under pressure. The last thing I want to highlight with the extrusions is everybody's always complaining. All the balloon guys, at least, are always complaining to the extruders about the visual defects in the tube. And I'm sure, Steve, from a extrusion background, you've heard all the woes of
Yeah.
of the balloon guys. Things like draw lines and fish eyes and gels, and pitting or blisters on the tube. And all things that are really undesirable because we're not really changing the extrusion, right? We're not fully reflowing it. We're just blow molding it. And so I wanted to give a little bit of some visualization to what we're talking about. So here you can see, this is the same tube, tube stage and then balloon stage here, right? After it's been formed, you can see the same draw line is present along the length of the balloon. And sometimes when we burst test these balloons, you'll see the burst run right through that draw line. Same thing here. This is a balloon surface, tube surface. You can see, the blistering forms this weird kind of shape in the outermost surface of the balloon. This is a PVAX balloon, so you can see this. There's this little kind of crystallization of the lamellae on the surface as well. Another, see FM flowing into the balloon. That FM, after axial and radial stretching, breaks apart, kind of gets surrounded by some gels. It makes this defect here that could potentially nucleate into a burst. And then a gel defect, under microscopy, scanning electron microscope, right? Like these are real defects that we're seeing in our balloons. And well, sometimes they are due to processing, and I'll run into that again a little later. A lot of the time, we can correlate that to defects that we're seeing in our tubes as well. So, extrusion is probably the most critical component of the whole balloon blowing process.
Right.
So, next phase of our journey here is the blow molding. And there's really, 3 key factors to medical balloon blow molding. It's heat, pressure, and stretch. Every step of our recipes that we're making to blow a balloon is a combination of those 3 things, right? They're all kind of linked together with timing. So the timing is pretty critical, but, we just heat our balloon, pressurize it, and we stretch it. The key thing to remember here is that we never fully melt the material, right? We're just heating it up to a point where it's soft enough for us to expand it. And sometimes even, we'll expand or we'll blow the balloon without heat, and then we'll heat set it in that state as well. So at the bottom, Steve, you were asking about the ultra compliant balloons. So that's an example of a polyethylene tube that we're free blowing in open air. And we do that just to kind of see how it's going to blow. And one of the things that's really interesting is that you can measure the diameter of the tube that the tube goes to in its inflated state. It'll inflate and it'll actually stay there for the most part, right, until you overinflate and it pops. And we actually measure the diameter at this inflated state, and we found that the same dimensions in the tube, right, can actually yield 2 completely different blown dimensional states, right, depending on your temperatures, your residence time, your drawdown ratio, tank gap, all the different extrusion parameters affect the performance of this tube. And so just because you're able to hit the dimensions of the tube doesn't necessarily mean that tube is going to work for blowing a balloon. And we've actually kind of shown a pretty good correlation of, we free blow the tube and we measure the diameter, we actually won't be able to form a balloon larger than the measured diameter. You might be able to stretch it just a little bit with some heat, but it's not like you're going to be able to blow a balloon that's 2 millimeters larger than the free blown diameter of their tubing, at least when it comes to compliant balloons. So that's kind of an interesting little thing we did on the bench here to show really the criticality and differences that you can see just in the material, even though it's the same dimensions.
Interesting. So true about the extrusions. You could, if you're a balloon former that doesn't have in-house extrusion, I imagine it could be challenging at some times working with different vendors who can meet the dimensional specs, maybe elongation, but different extruders, different screw designs, temperature profiles, die gap, quenching, pulling, all these parameters affect the mechanical properties.
Yeah, and it's really frustrating, especially when, just like extruders, we're also on tight timelines. And, we order a tube and, we hope it's the same as the last the last batch of tubing, and then we go to blow it. It turns out, we have to change our process to account for variations in that tube. So, it's always a give and take, right? We want to make sure that, all the extruding guys have fun, have, easy lives too. But, when we're blowing up our tube, the same tube, and we're not getting the same diameter, it makes things difficult for us too. Honestly, this might be the slide that I was most excited to share at MPP, because one of the most common frustrations in balloon blowing are these fisheye defects, and I know that when I was working at Switchback, we had projects that were plagued with these fisheye defects, and we tried so hard to understand them, um, and when I was looking into it, trying to do research online and talking to different people, it was kind of hard to get a picture of what they are and get a visualization of it. Um, and so we were lucky enough to embark on this journey to take some images of them under the scanning electron microscope and really do a deep dive into what they are. And so I'm kind of excited to share this. That we found that the fisheyes seem to be micro tears within the balloon wall that propagate from a nucleation point. Um, right, and so what you can see here is all the way on the left side. This is about a 2 micron defect. Right, there's no chance you're seeing that in with the naked eye or even under like 10x magnification. This is really tiny. This isn't showing up in your visual inspections. And you can see that it kind of starts to, it almost looks like a void in the tube, right? It's kind of in the balloon, right? It's really hard to imagine that this is in, a 2 thou wall polymer material, right? That you have this hole in there. Um, and you can see kind of how that potentially develops, right? As you stretch the tube more, depending on when that nucleation point formed in the blowing process into something that has more of these ripples coming off the sides, and then finally into the full fisheye, right? So this is a full fisheye. This is maybe about 100 microns long by 50 microns tall. And you can see these little tear marks on the 2 edges and, potentially, additional defects on the inside. And this is within a 2 thou, balloon wall, keep in mind. And, if we zoomed in, we kind of saw these tearing. That's how we really discovered this, right? Is we took a picture of the fisheye. We're like, oh, what are these little tear marks on the corners, right? Well, let's see what we can see on other areas of the balloon. And we were lucky enough to find potentially, an earlier stage fisheye, and then even this small little nucleation that your visual inspection isn't even catching, even under the polarized scope. So it's just really cool to be able to I don't know, finally have a visual for what a fisheye is looking like, and I don't know, and see if other people are seeing these same kind of defects, and I don't know if their studies kind of also line up with what we're seeing here. A little nucleation when you stretch it, with a stretch ratio of up to 300%, and then an expansion ratio of maybe 500%. It's a lot of stretching, and a small little dent in your tube might stretch and tear your balloon wall into a fisheye.
Nate, is that one of the reasons why somebody might use a multi-layer balloon? Just because of the additional layers, you have the confidence that even if you have a micro tear on one, that you have a backup layer. Does that have anything to do with it?
A little bit. I mean, it's you can still experience these tears in multi-layer balloons, and they're still definitely undesirable. We still definitely scrap out for fisheyes on our multi-layers. Okay. Really, what we're looking at with the multi-layers is the fatigue performance of the multi-layer balloons is second to none. We found that they fatigue a lot better than the single layer balloon, because often the multi-layer balloons sometimes use the same material, but oftentimes it's a combination of multiple materials, right? Like usually you'll have a nylon and a P-Bax, and you might even have like a nylon P-Bax and another layer of nylon or another layer of P-Bax. So you really get that great balance between the softness and more higher elasticity of a P-Bax material versus the rigidity of the nylon. We also use those a lot in like stent deployment, right, where that PBAX layer is going to provide additional friction, right? It's going to be a little bit softer against the tissue, softer against the stent, um, and but still maintain the rigidity and control diameter that a nylon balloon offers. And then the puncture resistance of a multi-layer balloon is also far higher than a single layer balloon. So there's a lot of reasons that we do that. This may be a small part of it. You have that additional redundancy, but like I'll actually compare this to something from that I learned with leads. Right, a lot of leads like to use multi-filar coils. Right, and there's a theory out there that like, oh well, if one of the filers breaks, then at least you still have your others. But in reality, if one filer breaks, all of a sudden you have a weak spot in your coil. Right. And it's not going to be very long before the rest of your coil breaks in that same location. And so if you have a defect in your multi-layer balloon, yes, it's going to, you have additional layers on there, but if it creates a failure point, it's still going to fail at that defect.
Gotcha.
Last thing I'll talk about here is testing. Testing with medical balloons is incredibly important. The rated burst pressure is the pressure at which 99.9% of balloons survive with 95% confidence. That's true for balloons using vasculature. This is defined by an FDA guidance, and the guidance is specifically for angioplasty balloons. But what we found is that FDA has been, or through our customers, that the FDA has been enforcing that guidance, that they want us to collect this level of data for the burst rating of the balloon. Really, for any balloon that's in the vasculature, it's a little different for balloons that are used in more peripheral applications, like ENT balloons, for example, where it's not, a burst in your sinus is not, quite the same as a burst inside of an artery or your heart potentially. But this is a really, really strict requirement. And we got to show with 95% confidence that 99.9% of our balloons are going to survive, which essentially means that we can't have a single defect in our balloon. If you think about the statistics of it, we generally plan for a standard deviation around 1 atmosphere. And if you have, an outlier in that increases your standard deviation, one early burst, you're basically scrapping your entire lot because the K factor that you have to multiply your average or subtract from your average, or you multiply your standard deviation by your K factor and subtract that from your average, right? That value, your buffer, has to become really high, and oftentimes, we'll drop the rating of that lot below the customer's target rated burst pressure, which just highlighting the criticality of defects in that, and this high-speed video that's kind of playing on the right. Maybe you saw burst oriented first time, but there's a pinhole leak in that balloon, right? And so that pinhole, right, you can see that form just a split second before the balloon bursts. And in a compliance balloon, right, that's probably nucleating from a defect or coming from a defect, right, that's failed, and then the balloon bursts there. So that was a really cool study that we were able to do.
It's a cool video.
Yeah, it is a cool video. I'm not quite sure why it's not looping here, but the other test, it did before. Yeah, it's cool. Maybe I'll go back and we can play it afterwards. But the next test that I'll highlight here is the compliance test. So we characterize the diameter versus pressure to show what the inflation of the balloon is going to look like. This is really, really critical when you're trying to deploy a stent or an implantable, like a replacement heart valve, because the diameter at which a stent is deployed to, or valve, is really, really critical. Right, it changes the hemodynamics of the implant quite a bit, right? Whether it's inflated a little bit more at a larger diameter or a smaller diameter, right? If it's bigger, maybe it's applying too much pressure to the vessel. If it's too small, it could dislodge, or potentially there's not enough fluid, blood that's passing through it. And so characterizing compliance is really critical. And any change in that compliance that we're seeing could also, have converse effects in the therapy that's being provided to the patient. And then lastly, but certainly not least, is the fatigue testing that we do on our balloons. Sometimes balloons are inflated and then deflated and then reinflated. And since we're pushing these polymer materials up to their limit, exposing them to high amounts of stress, right? Upwards of, I think even some of our highest balloons are at 30 atmospheres, right? Which, is over, uh, what is it? The conversion to PSI. You multiply by 14, whatever 30 times 14.7 is in PSI.
Okay.
It's a lot of pressure. um, and so we want to make sure that they're safe to be inflated and reinflated over and over again. So, we make sure to test the structural integrity. So, in general, balloons, they're engineered to meet highly strict requirements. We need to overcome manufacturing variation, both in our process, the extrusion process. So really, they're over-engineered, and we really have to understand where the limits are of all the materials that we're working with.
Yeah, that's excellent. Such a critical part of the overall process, kind of closing the loop, right?
Mm-hmm. Yeah, absolutely. Yeah, without testing, we really wouldn't know, how to design our balloons and whether or not our balloons are, are safe for use. It's pretty much the whole thing, just kind of revisiting medical balloon journey, right? Everything starts with extrusion, where, dimensions, concentricity, and the, mechanical performance of the extrusion are highly critical. Then we go to blow molding, right? Where we're taking that extrusion, we're stretching it, heating it up, and pressurizing it to the form factor that's best for, the balloon catheter, the application that's needed from the customer. And then, testing, super critical to make sure that, every lot that we ship out is, of the highest quality. And it's, trying to ensure that there's going to be no failures out there in the field.
Excellent. Yeah, excellent, Nate. Yeah, like I said, that was such a great presentation at MPP. I'm so glad you could share it to the broader audience. Not enough out there on balloon technologies and that journey, the manufacturing process that's so critical. So I really appreciate you sharing that with us.
Yeah, absolutely. Really excited to share this and share as much as we possibly can. And it's balloons are really it's really like a material science kind of thing, right? I never imagined that I would have to look into what goes into all of these engineered plastics so much as I did, and until I really started working on balloons. Even in leads, right? We were looking at bond chemistry and fatigue performance of silicone and urethane materials, but it wasn't really until I started looking into balloons that I realized, like, holy cow, this stuff is really critical.
Yeah, and back to the extrusion, which I'm so passionate about. There's such a difference between a PBAX or a nylon or TP extrusion that's used on a reflow composite catheter shaft than a balloon, right?
Yeah, absolutely. And even then, right, like, just it's so much more than just a spec sheet. Just because
Yeah.
your resin spec sheet says that it's got an elongation of so much and a stress at break of whatever megapascals, right? Once you put it through your extruder, everything changes, right? And you need to completely recharacterize it. And we understand that there's going to be some losses in any heat history process, like extrusion and reflow, especially, right? But understanding what the effects are and making sure that we're consistent between lots is it's a whole challenge of itself. Just the other day we were talking with one of our balloon extrusion customers, and we really came to the conclusion, highlighting that these balloon extrusions are engineered tubes, right? We're really engineering them. The diameters are not just picked out of thin air. Wall thicknesses, concentricity is very difficult to achieve when you're trying to make a super stretchy tube like that. And the process itself, it's just like any other manufacturing process that we're running in, for assembly. It's got to be well documented and highly maintained.
Engineered tubes. Plus, congrats on the, not so recent, but fairly recent expansion of a business platform for LightningCath and the balloon technologies. I know you guys do a great job in extrusion and FEP heat shrink and catheters. And now you have this new platform with balloon technologies, and you're doing a great job. So congrats.
Thanks, Steve, so much. I'm really excited with what we're doing here. I'll give you a little teaser of like what's to come, because we're moving so fast. We just brought in capabilities to machine prototype balloon molds. And so over the next few months, we're going to start rolling out, our rapid prototype program, where we're trying to cut balloon lead times into, down to just a couple of weeks for a custom balloon, right? Which we think that's going to be game changing for, at least our customers have given us the feedback that they want the ability to iterate faster and cheaper for balloons, and we want to give them that to them. So we're really excited about that. And then, the other cool thing that we've got going is, I think next week, we've got a PTFE extruder. It's going to be lifted up on a crane and dropped through a hole in the roof of our facility onto a tower. So we'll start PTFE extrusion line, hopefully, or definitely before the end of the year for sure. Hopefully by, fingers crossed, September, October timeframe.
Yeah.
Should be seeing some PTFE extrusion coming off that line. So
another tech platform. Congratulations. That's great.
Yeah. Thank you so much, Steve. It's so much fun to have the ability to work so quickly here at LightningCath.
Yeah. Speed is key, right?
Yeah. Speed is key.
Yeah. All right. Thanks again, Nate. Appreciate it. Well, I'm sure everybody's going to enjoy this podcast, and I'm going to have you on again, maybe early next year or something.
Yeah, definitely. We'll have so many more new things to share.
Yeah, exactly. All right. Thanks again, Nate.
Yeah. Thank you, Steve.